board. All right. All right, so 1.2, we're going to use a good bit of inductive reasoning in this section, looking at kind of a main emphasis section, number patterns. So might pop in, so we are 100% here. And a good bit of what we're going to look at in terms of number patterns in this section are number sequences in different types. So sequences. And we could spend an entire semester just studying number sequences. You have a starting point, and then there's some way to generate subsequent terms of said sequence. Subsequent numbers, but we'll call them terms. And but we're just going to kind of get an overview. So a couple different types that we'll look at. One we're going to call arithmetic. So if you have an arithmetic sequence, it has a common difference between successive terms. So whatever it's word difference twice has a common difference between successive terms. So any two terms, any two consecutive terms, that if I take the difference, subtract them, I'm always going to get the same difference, the same number every single time. So simple example, 3, 6, 9, 12, 15. Next term would be 18, so on and so forth. So that 6 minus 3 is 3, 9 minus 6 is 3, 12 minus 9 is 3, etc. The common difference there is 3. And then the other big one we'll look at, we're going to call geometric. A geometric sequence has a common ratio between successive terms. So that if I take any two consecutive terms and I divide one by the other in a certain order, I'm going to get the same number every single time. So example, maybe something like this: 3, 12, 48, 192, 768. Okay, so here, 12 divided by 3 is 4. 48 divided by 12 is 4. 192 divided by 48 is 4. 768 divided by 192 is 4. So I can find the next term simply by taking 768 and multiplying by 4. So, excuse me. So, but there'll be a few problems in homework where you're asked to identify, you're given a sequence and identify it as arithmetic, geometric, or neither. So you're just checking again, you have a common difference between any two consecutive terms or a common ratio between any two consecutive terms. Now, there are a lot of other types of sequences that aren't, either arithmetic or geometric. Of course, one we had already looked at was this one, which we refer to as the Fibonacci sequence. Now, then there are other sequences, such as that are neither geometric, arithmetic, or even Fibonacci. So throw one here. So let's say I had 5, 15, 37, 77, and 141. Okay. So if I were looking at this sequence here and I said, what is the next term of this sequence? If I went to look to see if it was first arithmetic, I would say quickly no. 15 minus 5 is 10, but 37 minus 15 is going to be what, 22. So right there, we don't have a common difference. If I looked at 15 divided by 5, that's 3. And 37 divided by 15, about what, 2 point something or other, but it's definitely not 3. So it's neither arithmetic nor geometric. It's certainly not Fibonacci. I can add the 2 consecutive terms to get the next term. So what I'm going to look at is maybe a technique we can use to find. It won't work for all, but it'll work for a good many, to find that next term, to figure out how to figure out what this would be. And what we're going to do is kind of like we were testing for, is it arithmetic? I'm going to go ahead and with the terms that I do have as a sequence, find the difference for each. That is, so 15 minus 5, we already said that was 10. 37 minus 15 would be 22. 77 minus 37 would be 40. And too much arithmetic in my head. So 141 minus 77, I get 64. And what I'm going to do from there is do it again with these. And ultimately, what I'm looking for is either I get to a point where I do have a row of common, all the same number, common differences, or a pattern, something that I can clearly see. It can, it's going 1, 2, 3, 4, or something like that, but a clear pattern. So continuing on, 22 minus 10 would be 12. 40 minus 22 would be 18. And 64 minus 40 would be 24. Now, if I went again and I looked at 18 minus 12, with one more row, I would get a 6. And then 24 minus 18, I would also get a 6. So once I find that common row of here, what I can do is assume the next number in that row would also be 6. And now I can build backwards. That is, I can say, okay, then right here, I would have had to have had a 30, because 30 minus 24 would be 6. And then the next term right here, I would add 30 plus 64, and I would have 94. And then I get to what the next term of the actual sequence would be by going 141 plus 94. And that would give me 235. Okay, and this method that I'm using right here is referred to as the method of successive differences. And so it's used to find next term of a sequence, but in this fashion. Any questions on method of successive differences? All right, so in homework problems, it'll say use the method of successive differences to find next term or maybe next 2 terms. And, I could from here find as many as I want simply by, keeping to repeat this. I would assume again, this is 6 and then this is 36 and so on and so forth. You build up to find that next term. All right. Any questions on the method of successive differences? All right. So, you can see where I'm using inductive reasoning, however, by just simply I'm looking at once I hit here and I have this common row of numbers, I'm looking at a series of repeated pattern and assuming that next one will be, it's a fairly strong argument, not a proof, but, fairly strong. But definitely the reason is inductive. All right, so any questions on this? All right, so I'm going to now talk about kind of like related to sequences. Talk about some summing formulas, one of which we have already looked at, albeit briefly. And that is if I add consecutive counting numbers, and now I'm going to use ellipses and say up to some counting number going consecutively. And I'm just going to write that's a letter N. Now, and this is important when we look at some other summing formulas. What N is the number of terms being added together. Referred to as the ordinal number. You don't have to really remember that term ordinal number, but that is what it's called. But again, it's simply how many terms have I added up in this particular sum? And there are oodles and oodles and oodles of summing formulas. We're just looking again at a few just to get an idea of them. Now, Gauss, again, as a little kid, 6-year-old boy, added up the numbers from 1 to 100, figured out a pattern way to do that. But when he was about 20, he figured out that if I take the number of terms that I've added up in this particular sum, which, since it's consecutive counting numbers starting at 1, if I add it out to 200, I've added up 200 terms. And I could plug 200 into this formula, and that would, in fact, be the sum. And then, of course, he had a deductive proof for this, but this was, in fact, summing formula. So, again, this is one that we have already kind of looked at. So we want to consider another one. And so what I'm going to do to get this next one is use a little bit of inductive reasoning and looking for a pattern. So let's say so I'm going to start with, excuse me. Looks like this. All right, so simple little equation, 1 equals 1 squared. 1 times 1 is 1. So that is true. I'm then going to look at 1 plus 3. Now 1 plus 3 would be 4, but 4 is a perfect square. That is, it is 2 squared. And 1 plus 3 plus 5. Now if you add those up, you're going to get 9. But 9 is a perfect square. It is 3 squared. If I add up, then it would appear what I'm doing is starting at 1 and adding up consecutive odd numbers. I would start to predict this is going to be a perfect square. The next perfect square is 16. And in fact, 1 plus 3 is 4, plus 5 is 9, and 9 plus 7 is 16. And that is 4 squared. Also note that in adding up to consecutive odd numbers, starting at 1, if I add up the first 4, that is, I've added up 4 terms, or n is 4, the sum was n squared, or in this case, 4 squared. So I would predict if I add up then the first 5 odd numbers, the next one would be 9, that this would be 5 squared. Well, as a matter of fact, that does add up to be 25. And so using inductive reasoning, I could now conclude that if I add up consecutive odd numbers, how many ever I add up, if I added up the first 125 odd numbers starting with 1, that sum would be 125 squared. And that again is reasoning this inductively. It's not a proof, but it seems very likely for sure. So let's see if we can write up a formula for this. If I had 1 plus 3 plus 5 plus 7 plus 9. So I've established a pattern of adding up consecutive odd numbers. Now, this is where it gets a little trickier. I have to represent that what we call the nth term, because we're writing up a general formula. Now, what we do know is it is the number of terms added here squared. That would, right there would be the formula, just simply n squared. But how do I write this nth term? And so for these kinds of summing formulas, we have to figure out a way to write that term in terms of n, the number of terms that I've added up. And every summing formula looks a little bit, different. This was the simplest one because n would be, in this case, the number of things I have added up. So what I'm going to do is just put it in here. I'm going to use parentheses to kind of keep it grouped together. But in the case of this one, it's 2n minus 1. That would be how we represent that nth term. Now, just to get an idea of what I mean, if I add up the first term, which would just be 1. Now plug 1 in here. 2 times 1 is 2, and 2 minus 1 is 1. If I add up the first 2 odd terms, or remember, this thing is going to give me that last term of the sequence. So let's say I add up the first 5 odd terms, starting at 1. So the 5th term in that sum would be 9. If I plug 5 in here, 2 times 5 is what? 10. And 10 minus 1 kicks me back to 9. So that's how it works. Any questions on this so far? Now let's do just an example of using this formula to find a, say we went 1 plus 3 plus 5 plus 7 plus 9. Again, this is just establishing, we're adding up consecutive odds. And let's say I take this out to something ridiculous, 357. So fairly big odd number. Now, so I want to find this sum using this formula. So think about it. I know what I need to figure out is how many odd numbers I've added up, starting at 1. It's not 357 of them, roughly half of that. But if you take an odd number and divide by 2, it does not divide evenly. So it comes down to finding in how many exactly odd numbers did I just add up here. And to do that, so I'm going to write a little to find in the case of adding up consecutive odd numbers. We're going to take last, we'll use a pound sign there, or hashtag, last number of sum, add 1 to it, and then divide by 2, and that will give you n. So for us, that would be 357. So I add 1 to it. That gives me 358, and then I divide by what? 2. And that will be the number of odd numbers that I have added up. So if I do that real quick, I'll have 358 divided by 2. And I get 179. So I have added up the first 179 odd numbers. And so from there, it's just go over and say, well, the sum then has to be 179 squared. 179 times 179, which in this case works out to be 32,041. Any questions on that one? Going once, going twice. Okay, so one thing to note about how I said to find the number of odd numbers you've added up here. If I had just given you, we have a lot of room here. If I had just given you the little algebraic equation, 2n minus 1 equals 357, and said solve that, how would you solve this for n? Well, you'd first add 1 to both sides. And then you would divide both sides by 2. So me just saying to do this, really what it is solving that linear equation, taking that last nth term, setting it equal to this to find n. And then once you find n, you square it. All right. So let's look at a couple others. Again, because I said there's oodles and oodles of them. So this next one, again, it's just to have, so we have an example of a few. If you take adding up consecutive counting numbers, 1 plus 2 plus 3 plus 4 out to n, but take this whole sum and you square it, that is the same thing as 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, and then out to, that one just seems crazy, but it is true. That this one would work every single time. And then one other, and I don't believe there's any, because this one's not in the book at all, or wouldn't be within the homework, but we did consecutive natural numbers. We did consecutive odd numbers. And so it'd be worth, what if I were looking at consecutive even numbers? Starting at 2. Now the nth term here is a little easier. It would just be 2n. But its summing formula is simply n times n plus 1. So that if I were just to add up, say 2 plus 4 plus 6 plus 8, let's just do one that we could actually mentally add it up. That would be 6, and then 6 plus 6 is 12, and 12 plus 8 is 20. Now, if I use the formula, I would have added up the first, 4 even numbers. And if you just took 8 and divided by 2, you get 4. I mean, and that's the easiest way to figure out how many even numbers you've added up. Just simply take the last one and divide it by 2, or essentially you're setting it equal to 2n. So I've added up the first 4, which means it would go into this formula, and I would end up with 4 times 5, which in fact is 20. And again, there's more, just oodles and oodles and oodles, thousands of different kinds of summing formulas. We're just looking at a few. Any questions on the summing formulas? Okay, if not, I'm going to look at one other type of number sequences. So, and these are all going to be this next group of number sequences we're going to look at are going to kind of all be tied together, and actually even steps back a little bit and with what we had studied last unit, and that is Euclidean geometry. All right, so the first two sequences we're going to look at, I'm going to have to draw a little bit here. And that's just a point. And it's going to be the first term of this new sequence we're going to look at. We'll get a 1. All right, so to get the next term of this sequence, what I want to say is I'm going to take that dot and say, how many more dots do I need to add to it to form a triangular shape? Well, I would need 2. I would need 1 here and 1 here so that I could play connect the dot and I've got a triangle. And then say, well, how many dots did I need total, or do I have total? And you would say 3. All right, and that's going to be the next term of the sequence. So it kind of gives me an idea of how I'm going to find each term of the sequence. I'm going to take the previous triangle and then say, how many more dots do I need to add to make yet a bigger triangle? In this case, I would need 3. And then I would have a total of 6 dots. And we'll do this one more time. Screen down a little bit. So I take this, where we've got our 6 dots, and then say, well, how many more dots do I need to add to make yet a bigger triangle? And I would need 4 more, and that would now give me 10. All right, and so I now have the first 4 terms of this sequence. What would be the next term of the sequence based on what you have seen? And this would be using inductive reasoning. What would be the next term of the sequence? You guys can just type it in chat or verbally say it. What would be the next term of this sequence? Take my glass triangle. Yeah, somebody. Yep. And it would be 15. So you would take the 10 here, and then this is a question, how many more dots would I need to add? And I would need 5 more, and I would have a total of 15. And so what I'm going to conclude is to get the next term of the sequence. So here I added 2. Here I added 3 to get here. Here I added 4. Then I added 5 to get the 5th term of the sequence. So I would add 6 to this, and that would give me 21. Then I would add 7, which would give me 28. And I will go 1 more. And I would add 8 to that, and that gets me to what? 36. So make sure I added 6, added 7, added 8, etc. All right, so this number sequence that we're looking at is called, you may have already guessed, but these are the triangular numbers. And you can see where they get their name. The Greeks in antiquity, they were the ones who were looking at these number sequences originally, and again, they could base them off geometric shapes, and in this case, polygons. So I'm going to look at the next sequence, and I'm going to start it at 1. In fact, all of these are going to start at 1. And this time, I'm not wanting to build a triangle, but I'm wanting to build a square. How many dots would I need to add to my 1 dot? to get a square, I'd need to add 3 dots. And then that gets me to the next term of the sequence, which would be 4. And then I would play that same game. I would take my original square and say to myself, how many dots do I need to add to that to form yet a bigger square? And I would need 1, 2, 3, 4, 5. And that gives me a total of 9 dots. And we'll do one more. If I take my original square from my last term, 9, and say, well, how many more dots would I need to add to form yet a bigger square? I would need 1, 2, 3, 4, 5, 6, and 7. And then I would have a total of 16 dots. And then it should not be lost on you. When I look at this sequence, these are all perfect squares. And to find the next term, it looked like I added 3 here to get that. Then I added 5 here to get that. And then I added 7 to get that. So I would conclude I would need to add 9 to get to the next term. And that's exactly what I would need to add. And so I'm adding consecutive odd numbers, what we had just looked at. And the next one, I would add 11. And that would get me to the next term of this sequence. And as you might have suspected, these are referred to as the square numbers. All right, so I'm going to do one more. We're going to start with 1 dot, and I want a little more room. So 1 dot here. Well, it would seem reasonable. I did what 3-sided figure, triangle, a 4-sided figure, square. So how about a regular pentagon, 5-sided? And this is where my artistry definitely fails me, but I will do my best. I want to form a pentagon. And so I'd start with my 1 dot and say, how many more dots would I need to add to get a pentagonal shape? And I would need to add 1, 2, 3, 4, and would give me a total of 5. And I want to flip back the page just for a second. Notice that second term was 3 in the triangle numbers. Second number of the sequence here for the square numbers was 4, 4-sided figure. Second number of the second term here is 5, 5-sided figure. And that, no accident. But I had to add 4. All right. So I'm going to try to get this next term. I will try to draw it the best I can. But goal would be the same. I want to make yet a bigger 5-sided figure pentagon. All right. So how many dots would I need to put in here? Get yet a bigger one, 2, 3, 4, 5. Again, I'm definitely going to try it again after that. But 1, 2, 3, 4, 5. I'm missing one. I just can't. I very rarely do the pentagon. I apologize. Let me try again. 1, 2, 3, 4, 5, 6, 7. It's 7 dots that I need to add in here. 1, 2, 3, 4, 5. Sorry, but I had to add in 7 dots. And that gets me the next term of the sequence of this particular sequence, and it would be 12. Now, without drawing yet a bigger pentagon, which I think I would be more damage than good, let's see if we can figure out just a pattern to this. It went 1 plus 4 to get this term. To get this term, it's actually 1 plus 4 plus 7. That is, to get that third term of this sequence, I went 1 plus 4 plus 7. So to get the fourth term, reasoning inductively, what do you think I would add here? To get the next term of the fourth term of the sequence, what 4 numbers would I add up? And that is correct, Justin. It would be 10. It's like by gaps of 3 now. And so the next term of this number sequence is 22. And if I wanted to get the fifth term, I would then add 13, and which would then get me to 35. So on and so forth. So it's adding up consecutive numbers starting at 1 or consecutive by gaps of 3. And as you might have suspected, these are referred to as the pentagonal numbers. Now, past pentagonal numbers, there are hexagonal numbers. That would be a sequence of itself. Heptagonal, octagonal, nonagonal, so on and so forth. These are all put under one heading called the figure numbers. So triangular, square, pentagonal, hexagonal, heptagonal, octagonal, nonagonal are all under the heading of figure numbers. And so kind of tying this all together, what I want to do is I want to write out those first triangular numbers, which were 1, 3, and then 6. And remember how I was generating each of the terms, and without drawing pictures, it was just really adding up consecutive natural numbers. So that is, if I want the fourth term of the triangular numbers, then the fourth term would be 1 plus 2 plus 3 plus 4, which is 10. Fifth term would be 1 plus 2 plus 3 plus 4 plus 5, and then plus 6, and then plus 7, and then plus 8, etc. And again, these were my triangular numbers. The square numbers was adding up consecutive odd numbers. 1 plus 3 got me to my next term, which was 4. Then 1 plus 3 plus 5. Then 1 plus 3 plus 5 plus 7. 1 plus 3 plus 5 plus 7 plus 9. And plus 11. Plus 13. And then plus 15 will get me to here, which would then be what, 64. Okay. All right, patterns galore in this. The pentagonals. So remember, it went by gaps of 3. I would go 1 plus 4. 1 plus 4 plus 7. Next term. 1 plus 4 plus 7, then plus 9, which gets me to here. So if I add 1 plus 4 plus 7, plus 10, that was my bad. So plus 10, then plus 13. And then plus 16 for here. And so 35 plus 16. 51. So then so we went 1 for the sixth term here. It was 1 plus 4 plus 7 plus 10 plus 13 plus 16. So I would then add 19. Which gives me 68. Is that correctly? 7. Checking my arithmetic here. 13 plus 16 plus 19. Yeah, I thought something was off. So 1 plus 4 plus 7 plus 10 plus 13 plus 16 plus 19, adding up the first, starting at 1, first 7 numbers by gaps of 3. That should have been 70. That number's okay. All right. That should have been 70. All right. And it's probably enough there. But these were the pentagonals. So the next would be the hexagonal numbers, 6-sided figures. Now here I added what kind of the pattern I'm now seeing here. To find the terms here, I'm adding up consecutive counting numbers started with gaps of 1. Consecutive counting numbers, but by gaps of 2, 1 plus 3 plus 5 plus 7. Consecutive counting numbers here by gaps of 3, 1 plus 4 plus 7 plus 10, etc. So this I would expect by gaps of 4. That is, I would add up 1 plus 5 to get the second term here. And so the third term would be 1 plus 5. If I'm adding up by gaps of 4, then I would be adding a what? A 9. And 9 plus 6 is 15. And then the fourth term here would be 1 plus 5 plus 9 by 4. Then I would add 13. If I added 13 here to 15, I'm going to end up with what? 28. And so the next term would be 1 plus 5 plus 9 plus 13. Remember, we're going by gaps of 4, so I would have to add a 17. And 28 plus 17 is 45. But can you make an observation now that I've got the triangular numbers here, the square numbers here, then the pentagonal numbers here. Now I'm putting in the hexagonals. Look at the column that I'm forming here. Second term, 3, 4, 5, 6. This third term, notice they go by what? Gaps of 3. Then gaps of 6. Then gaps of what? 10. Going down the columns, those gaps are what? Triangular numbers. I mean, there's just patterns all over the place. So I would expect then this should be going by gaps of 15. Well, 21 plus 15 is 36, and 36 plus 15 is 51. So I could actually find the next term here by taking this and adding a 15. And then this, notice, is by gaps of 21. So, and so on and so forth. Put in a few heps and a few octs. So if I put in heptagonals, I would suspect here I'm going to be adding by gaps of 5. 1 plus 6 is 7. Then 1 plus 6 plus 11. And adding 11 to here is 18. And notice that falls right in down the column by 3. Octagonal, this would have to be 8. 1 plus 7, gaps of 6 between the two numbers I'm adding up. 1 plus 7, and then the next number, if I'm going by gaps of 6, would have to be a 13. And 13 plus 8 is 21. And again, that gap of 3 going down the column. There will be a problem in the homework where you're gonna fill out a whole table like this. Then you can use those number patterns that we have just observed here to do that pretty quickly. Now, since all of these, sequences, finding individual terms is a result of adding up some numbers, that is summing formulas. The first two we have summing formulas for. This was adding up consecutive counting numbers starting at 1, gaps of 1. And so if I had, wanted to find the 856 triangular number, I wouldn't want to have, all I really need to do. And so is put it in that summing formula for consecutive counting numbers, which was n times n plus 1 divided by 2. So if I wanted the 856 triangular number, I would plug it in to this formula. And this is just red T sub n, and the n was 865. I wanted to add up the first 865 odd numbers. Square numbers is found by adding up consecutive odds. So that was n squared. If I wanted the 865th square number, 865 squared. So now pentagonal numbers were found by adding up, starting at 1, but by gaps of 3. That is 1 plus 4 plus 7 plus 10 plus 13. And so to have a formula for the nth pentagonal number, you would need to know the summing formula for this one, which we haven't talked about. And then you would have to think, well, all of these would have to have summing formulas. But by pattern, if you can remember the one for pentagonal, you can get all the rest of these. That summing formula looks like this for this one right here. It's n times 3n minus 1 divided by 2. So kind of, looking at if I wanted the fourth term, which we know is 22 for the pentagonal numbers. If I plug 4 in here, just to verify that it works, this should come out to be 22. This would be 4 times, that would be 12 minus 1 is what? 11 divided by 2, and 4 times 11 is 44, and 44 divided by 2 is 22. Now I said, if you can remember the pentagon, you can get all the rest of them. Now you have the advantage, since we are living in the virtual world right now, when we did get to a test on this, you can have your notes. If we were back in the classroom, I've always tested this, just for memorization skills. You would have to remember this on the test if we were in the classroom. However, again, there's an easy pattern way to remember all the rest of these. If you can remember the pentagonal, the hexagonal, which is adding up 1 plus 5 plus 9 plus 13 by gaps of 4, it looks like this. And notice all it did was increase this and this by 1. The heptagonal formula is n times 5n minus 3 divided by 2. And so, yep, you would suspect that the octagonal would be n times and then 6n minus 4 divided by 2. So I didn't put nonagonal down there. There will be a problem dealing with nonagonal. But if its formula would be n times quantity 7n minus 5, all divided by 2. In the homework, there will be some problems dealing with these figured numbers we've been discussing, where you're one asked to build a table like this, one asked to find such and such term, find the 86th octagonal number. And then there's also problems where you're just looking at, again, there's oodles and oodles of patterns here. Something like this: if I add up 2 consecutive triangular numbers, what kind of number do I get? Well, 10 plus 15 is 25. 15 plus 21 is 36. 21 plus 28 is 49. So using inductive reasoning, just by looking at a series of examples, every time I add up 2 consecutive triangular numbers, I get a square number. And then there'll be some other numbers or other problems kind of doing the same thing, examining some patterns. There will be one problem in there where they give you a circle, and looking at putting points on the circle and generating. Actually, I'm going to go just try to find the number of the problem. Find it. It's within the method of successive differences problems. This one's always, it's number 11. So you might just want to put a little note, number 11. Almost always gets asked about it, but it's using method of successive differences. That is pretty much, have covered everything in 1.2 today. And so I'm going to assign 1.2. Get that set up. And today is the 16th, so I'm going to put 21st as the due date. That would be next Tuesday. It's due date. And so 1.2 is assigned. It is a lengthier homework assignment, though I'd say about half of those are fairly quickly done. And then there's some that will take a bit more time, like number 11. Let me